Good morning, good afternoon, everybody, depending on where you are. Welcome to the Distributed SQL Summit talk about SQL workload isolation in containerized multi-tenant environments. My name is Radek Gruchalski, and I'm a software engineer and managing director at Klarrio GmbH, a sister company of Klarrio with headquarters in Antwerp, Belgium. We build software to spec for our clients. And one of our clients is KPN, the Dutch telecom. This talk is based on the work we've done for KPN. They sponsored the work. Without them, it would have not happened. And I wanted to thank them for letting us get to this stage. Within the Klarrio team, and shout out to team Dominic and Hert, I am responsible for core Yugabyte feature investigation and core rollout. Some of you may know me from the community spotlight, Yugabyte community spotlight back in July. A few words about KPN Data Services Hub. A few years ago, a partnership has been formed by the government of the Netherlands to bring a number of industry experts in road traffic and road traffic infrastructure to investigate how to improve the traffic congestion situation in the Netherlands, as well as investigate use cases like time to green and traffic priority at the intersection. KPN has been selected as an infrastructure provider for this partnership, and KPN has commissioned Klarrio to build what became Data Services Hub, which is a data streaming real-time multi-tenant cooperative platform. Data Services Hub allows the members of the Talking Traffic Partnership to securely work and exchange data streams to which they hold the ownership of the data sources of these streams. It's a real-time multi-tenant streaming first platform built on Apache Kafka and Apache Mesos, and it can be deployed in private, public, and hybrid environments. The platform is multi-tenant. The tenants, the companies, bring their own containers onto the platform. They deploy it on a shared infrastructure. And whenever they need to cooperate on the use cases, the data is being exchanged through a message bus, as mentioned, built on Apache Kafka. Today, KPN uses Data Services Hub for a number of internal and external use cases. A few months ago, we've been approached by KPN to investigate, design, and build the multi-tenant self-service SQL solution for Data Services Hub. We selected a number of requirements. We put a number of constraints on us to work within for this feature. And some of the most interesting things are PostgreSQL compatibility, be able to reuse as much of existing tooling as possible. Not having to build tools is definitely an asset. It should be easy to monitor and audit. The tenants should be able to manage their own objects, database tables, within their database tables, views, potentially create their own roles and manage access to the objects they create. We wanted to have the ability to potentially ingest data through Kafka and also publish the data back on Kafka. One of the interesting aspects was something that was labeled rate limits. Now, in the context of an SQL database, rate limiting doesn't really make much sense. It's very difficult to control, for example, throughput or a bandwidth or a number of certain SQL statements that a tenant may execute. So as we started looking deeper into this requirement, we quickly realized that what the requirement really is about is to be able to commit a certain amount of compute resources to a tenant whenever a tenant will have a query that is slow or requires a lot of compute. If the resources underneath are shared between multiple tenants, that will inevitably lead to the congestion and to one tenant affecting the service level availability for other tenants. Being able to potentially not locate the data of different tenants next to each other would also be an asset because of PII or GDPR data requirements. So obviously the question is, why not to just use PostgreSQL? With PostgreSQL, this would be really straightforward to implement. We would have a single database server for a tenant, for a company where all the users of this tenant would be connecting to. So that concept of multi-tenancy then becomes a non-issue because there is just not a situation where one tenant connects to another tenant to run the workloads next to each other. That's not really a problem in this case. It became a problem a little bit further. We come back to this. With PostgreSQL, the problem is it's not a highly available database. So building a highly available PostgreSQL solution involves having a number of servers, number of PostgreSQL servers, where one of them is a master replica receiving all the reads and writes. And then we have a number of standby replicas, which are replicating from the master, such that in case of a master failure, another instance can take over. This taking over happens through a component, usually a load balancer in front, which has to detect that the current master is unavailable and has to manage the election of the new master and then manage the failover of the traffic. Some of these solutions for PostgreSQL high availability take advantage of consensus mechanisms like etcd in order to make sure that the data is properly replicated. This replication usually implies that the complete database server has to be replicated, which leads to having to maintain multiple nodes where all these nodes have to be able to fit the biggest available node within that environment. Now, having to maintain that many moving components for each tenant adds a lot of constraints and a lot of additional work onto the site reliability engineering team. It's not really easy to manage. So we were not really in favor of that. We come from a distributed background with Kafka. We like distributed systems. So we started looking at the alternatives. We looked at RDS, we looked at Cloud SQL, we looked at Cloud Spanner, we looked at databases like CitusDB, CockroachDB, and YugabyteDB. Some of the alternatives were rejected because we wanted to be able to run the solution on premise. So the cloud offerings would just not work in that case for us. Other alternatives, the licensing wasn't really permissive to run this as a service, as a self-managed service on premise. And YugabyteDB was the database, was the only alternative that would fulfill all these additional requirements of running on premise as a self-service. PostgreSQL, we already rejected. We're not really in the business of building distributed databases. There are many alternatives available out there, but each one of them is not really easy to maintain in the current state of art. As we selected the database that we wanted to use, we decided to focus on the use case of this resource allocation. And YugabyteDB has three properties that are very important to this one. So let's focus on these properties first before we jump into how we decided to build it. The first one is the actual overall architecture of YugabyteDB. YugabyteDB has two components. It has the master servers and it has the tablet servers. The master servers, for this use case, we can largely ignore. Within the cluster, they fulfill a role of essentially an address book. They know what data resides on which storage node. And the tablet servers use the data from the masters to then coordinate the query execution and planning. The tablet servers are the ones that store the actual data within the cluster. And the tablet servers, each one of them is running PostgreSQL. This is another aspect we like about YugabyteDB. It is using an actual PostgreSQL 11.2 engine under the hood. When we create tables in YugabyteDB, these tables are split into so-called tablets, which are essentially little partitions. These partitions are distributed across the complete cluster or only selected nodes within the cluster, such that in case of a single YugabyteDB node loss or multiple nodes, depending on our replication factor, we don't lose ability to insert or read data from these tables. The second element that is very helpful to us is a feature that was implemented in Yugabyte 2.7, YugabyteDB 2.7 back in, I believe, May 2021. And it's a take on PostgreSQL table spaces. In PostgreSQL table spaces, we can instruct the database to put selected objects within a dedicated directory that is available to the storage to a single PostgreSQL instance. YugabyteDB takes this concept one step further, and it allows us to treat individual T servers as the targets for these table spaces. So in YugabyteDB, the table spaces is groundwork for a feature called geo-partitioning, where we can carve out individual geolocations as the targets for where the tables or individual rows from the table is going to end up. Building on the concept of the table space, we come to a conclusion that we can constrain the query execution to selected table spaces. So when we look at the table spaces, they have this very interesting property that the tables, once we create a table space and we create a table and we assign it to selected nodes, and as an example here, we have a cluster that has 3 masters and 9 T servers. This cluster is split in 3 regions, and we create a table assigned to a table space within 1 region. When we execute a query, an SQL query against this table, that query will be executed only by the T servers on which the tablets for that table exist. So in this case, region 2 or region 3 will not be involved in executing a query against DB table 1. And this is what allows us to think of the geo partitioning as a narrow use case for a much wider thing, which we can call a workload aware placement. Our locality becomes a workload, and we can select a number of physical nodes within the cluster, and we can instruct YugabyteDB to execute these workloads and everything what is related to these workloads on these individual T servers. So in our case, going back to the Data Services Hub use case, multi-tenancy, if we were to, if we had the ability to instruct the database in such a way that all the objects of a given tenant are stored only on selected tablet servers assigned to that tenant, we would essentially achieve the workload isolation for a multi-tenant use case. We decided to investigate this a little bit further. It sounded like a really good approach to solving this problem. So we've built a test cluster, and we architected in the following way: that all the tablet servers reside within one single cluster. They have a shared set of master servers. For each tenant, we create a traffic reverse proxy, which gives a unique host name for each tenant. The network layer separation within the Data Services Hub ensures that only that tenant can connect to that host name. The traffic component allows the connectivity and load balances the PostgreSQL TCP traffic only to the T servers of that particular tenant. So to the tooling, it looks like standard Postgres, but in the backend, we get the proper data distribution and replication provided by YugabyteDB Raft mechanism. The T servers of other tenants cannot be accessed by that single traffic of another tenant, so that the data locality and the workload constraint is effectively enforced on this level. We have to solve a couple of other small problems that are still not covered by our implementation. I mentioned before, PostgreSQL is not really a multi-tenant database, and in this case it now matters because we have a set of almost shared PostgreSQL instances. YugabyteDB treats them as one big database. There are a couple of schemas and a couple of table spaces within PostgreSQL installation which are public and to which access cannot be easily revoked from users connecting to YugabyteDB. So if we look at an example of a user creating a table, for example, in a PG default schema or a PG default table space, that table would get split into tablets, which would then get distributed across the complete cluster, and potentially some of these tablets would end up on T servers to which the tenant physically cannot connect because his traffic reverse proxy does not simply does not load balance to this installation. So to solve this problem, we decided to use PostgreSQL extensions. So the great thing is YugabyteDB is Postgres under the hood, so extensions work. We built a process utility hook, which looks at the DDL statements and anything that is schema or table space aware. We validate that the tenant is interacting, or the users, the roles created by the tenant are interacting only with the objects that the tenant has access to. Originally, when we were looking at extensions, extensions worked, but it was not possible to easily enable access or enable loading of custom extensions to YugabyteDB. So we fixed that. We've contributed this back. So today anybody can load their extensions into YugabyteDB. So thanks to that, our tenants can manage their own permissions, their own access to their own objects, so the role-based access control becomes fully functional for the tenants. The second problem that we still wanted to solve was the ability for the tenants to share the data between each other. So we've already covered the fact that it's a multi-tenant solution and use cases are cooperative. Standard way of doing this in the Postgres world is to use Postgres foreign data wrapper extension. At the time when we started looking into YugabyteDB, foreign data wrapper was not supported. We have since then contributed foreign data wrapper to YugabyteDB, and it enables almost fully functional Postgres foreign data wrapper extension support. So that will be available soon in a beta release of YugabyteDB. So we found that as we were working on this feature, we found it very intriguing and interesting, and something worth sharing. This wider take on geo-partitioning as a concrete workload isolation sounded like something that the wider audience should know. With this, we are able to pin the workload to selected T servers, make sure that the data is located on the machines which are dedicated to our tenants. And we can also introduce additional table spaces for the tenants, such that when within one tenant there are workloads that need to be isolated, this can be easily achieved using this one awesome feature based on Yugabyte table spaces. That was my conclusion. I am ready to take your questions now. I wish everybody an awesome 2021 event. And if you want to continue talk about YugabyteDB with Klarrio, please reach out. Thank you very much.